C'est mon plaisir de recevoir Jean-Marie Stéphan, qui est présentement à l'Institut Camille en France, qui fait partie de l'Université de Lyon. Et tu es dans un labo ou un département de maths un peu, c'est ça, Jean-Marie?
Oui.
Ouais. Donc, Jean-Marie est très bien qualifié pour parler aujourd'hui. Et avant ça, Jean-Marie, he did a postdoctoral fellowship with Paul Fenley, right?
Yes.
That was at Virginia when Paul was there before moving to Oxford. And Jean-Marie, did you do another postdoc?
Yes, in Dresden.
In Dresden.
Yes.
Perfect. And now he has a faculty position in France. And today he'll tell us about StatMech and fermions through this interesting title, Fermionic limit shapes. And Jean-Marie, you'll speak in French or English? I forget to ask.
Prefer English, but
English, okay. So Jean-Marie will speak in English, so everyone.
Yeah, I'm less self-conscious in English, so that's why I slightly prefer it. Yeah, so thanks a lot for the invitation. It's a real pleasure to give this Zoom seminar. Yeah, so yeah, the aim of my talk would be essentially to explain you what I mean by this slightly mysterious title, Fermionic limit shapes. And this is this was work done with Savario Boccini, who was a student in Lyon who stayed for about a year in Lyon, and that was basically his main project. So perhaps I should give you an outline of my talk. So I will spend a little bit of time trying to explain my motivations, so the motivations for this work. And since this is, I understand, a reasonably broad audience, I will explain you some basics of fermionic techniques in statistical mechanics. Then I will talk about limit shapes, and in the final section, I will present you our new result on what I call fermionic limit shapes. So, and for motivation, let me discuss an example, which is arguably very simple. So this example is is a well-known model of statistical mechanics. So two-dimensional statistical mechanics. I consider some planar graph or planar lattice, and I put dimers on it. So here I show you an hexagonal lattice, which is drawn as a brick wall. Okay, so this is the same as the hexagonal lattice, except I draw it as a brick wall just for convenience. Okay, and on this lattice I put dimers. So dimers, they are these blue entities here or here or here, and they live on the edges of the lattice. And the rule of the game is so if you want, it's kind of a game. And the rule is that on each lattice site there can be only one dimer touching. So for example, the lattice site I circled in green, there is one dimer and only one dimer. Okay, and this is the rule. So this is the rule for my lattice, except, so I am allowed to break this rule here, okay, at the top and at the bottom boundaries. And I see those, if you want, as some kind of boundary condition where I can choose to put a dimer or not on all the vertical links if I want. Okay, and for convenience, I put some weight U for certain specific edges, which are shown in the picture. And for example, with this model, the probability, so if you want, if I have a lattice, I have lots of ways to cover it with dimers. There are many possibilities. I just show you one here in the picture. And the one in the picture has probability. So in principle, you could make it the model completely uniform. So every dimer covering has the same probability. Here I tweak it a little bit, and I put a weight U for certain dimers. And for example, the probability of the configuration shown in the picture is u to the 4 over the z, where z is the partition function. I have u to the 4 because unless I made a mistake, there is a u dimer here, a u dimer here, a u dimer here, and there is the last one, a u dimer here. Okay, so this is the model. So it's a very simple model of statistical mechanics. You can study it. And if you're a physicist, one of your favorite technique to solve this type of model is to use what's called the transfer matrix formalism. But before going into the details of this mapping, I just make the following observation that I can map my dimer configurations to actually a collection of particles moving upwards. And the mapping goes as follows. I just look at vertical lines. So I just look at vertical edges. Okay, so I just look at this one, this one, this one, this one, and I forget about all the rest. If I do that, I can define a particle to be not a dimer. So I put the red particle, which means particle, where I don't have a dimer. So for example, I have a particle here. So let me call it 1. I have a particle here. And whenever there is a dimer, I say there is no particle. Okay, so it's some kind of hole. So then I put a 0. Okay, and of course, if I can, if I look along given horizontal lines, there are many possible particle configuration. And since on each edge I can put a 1 or a 0, there are essentially 2 to the 6 here particle configuration. Okay, so this is the mapping. And the point is that this mapping, it's one-to-one in the sense that if I just give you the particle occupancies along each vertical edges. So here I erase the dimers. I put just the particles. I can easily reconstruct the dimer configuration. Okay, so you can see it. And why you can do that? Well, for example, here, since I know there is no particle, it means I have to draw a dimer here. Here, and there is no particle, I have to draw a dimer here and here, and so on. Okay, so if I do that, I can easily put back the vertical dimers. And now if I know all of those, I can also reconstruct the horizontal ones. And you can easily convince yourself that this has to be this. There is no other choice. Okay, so basically, if I give you a dimer configuration, it's exactly the same as if I give you a collection of ones, my particles, if you wish, that propagate upward. And of course, it's picturesque, but you can really see those as some kind of ones, and you see they propagate upwards. Okay, and they can move a little bit. So they don't have to go straight ahead. Sometimes they can go a little bit to the left or to the right. Okay, and this is what I want to exploit. Okay, so this is just to tell you that I have my configuration, and these are just particle configurations. And now what I do is well known to physicists. I describe those. So since I told you that there were 2 to the 6 configuration, it's very tempting to represent this using linear algebra and use tensor product to do so, because the 2 to the L, the number of configuration 2 to the L naturally occurs when you do tensor products of L, let's say 2 by 2 matrices or 2-1 vectors. Okay, and this is what I do in this slide. So it's I put all the formulas just so that it's self-contained. But basically, I see a 1 where I will write with physicist notation a ket1. It's just going to be this vector 1, 0. I have 0. So when there is no particle, it's this. Okay, and I represent my particle configuration. So if for example there is a 0, 1, 1, 0, 0, 1 along a given horizontal line. Well, I use this notation, and this will be the tensor product. Okay, so there are 2 to the 6 such configuration. Okay, vectors. Yes, and okay, so this is kind of a way to do nothing if you want, just a way to represent my particle configuration along a given horizontal line. But then I want to exploit linear algebra to actually, for example, compute partition functions or study properties of these models. And if you're and it's well known that you can do that using a mapping to fermions. Okay, so tensor products just is not enough. I need to map it to fermions. And the name that's usually associated to this, I mean, the first one that did it so they were trying to solve a different problem, but basically that's what they did, is this Jordan and Wigner. So this is called, what I show on this slide is called Jordan-Wigner transformation. And I define, so what's important for this mapping are this operator, so the most important is this operator CDAG, okay, which is just this 2-by-1 matrix. And the point is, if you apply this matrix to the vector 0, well, you get 1. Okay, so if you apply CDAG on 0, you get 1, and so on. Okay, so it's convenient to transform particle configuration to make 0 become 1, and so on. And the main operator in this game is this what physicists would call creation operator at site J, which is just essentially this operator which can transform 0 into 1s, but tensored with other guys that are simpler than CDAG. So on the right, it's trivial. It's like the 2-by-2 identity. So it means it doesn't do anything. And here you see there is this funny string of operator S. Okay, and this S is this thing here. So there are minus signs hanging around. So it's not quite the identity. There is a minus sign hanging around, and this is what makes those variables CDAG J what physicists would call fermions. And important, so you can do this exercise actually. So with this construction I gave you, it's easy to check that these commutation relations they are satisfied. And of course, if for example, in context matters context, this would be a given. So if I write basically C dagger I, Cj or operators like this, and I tell you they are fermions, immediately you know they satisfy this commutation relation, and this will be the one useful to solve this problem. Okay, and the point is that so far I still did not do anything, just if you want reformulation of the model, and I can also use my operators to describe my particle configuration along a given horizontal line. And for example, this particle configuration, you see there is a one at position 1, 2, 4, 6, and I can represent as creation operators acting on the special vector 0, okay, which is a vector with nothing. Okay, so all zeros. So I can represent all particle configuration with creation operators acting on the vacuum, but this is called the vacuum. Okay, so this is well known to physicists, but I thought it's nice to make the talk as self-contained as possible. And this is what I will use in the following. And of course, it's important that the operators they are applied in order, because you can pick up minus signs when you commute the fermions. You see, for example, here, if I commute Ci with Cj, I pick minus. Okay, so it's important that it's in order, because this vector would be also C dagger 2, C dagger 1, C dagger 4, C dagger 6. Okay. So, and the magic occurs because of these minus signs occur because of this string of S operator, which this is called Jordan-Wigner strings. Okay, so it's important to keep track of the order of fermions. Okay, good. And so with this as a given, you can solve this model with transfer matrix, with a transfer matrix. Okay, so this has some long history in statistical mechanics, so which started, I think, perhaps most famously with Onsager, who solved the two-dimensional Ising model of statistical mechanics, which is similar to the model I'm talking about here. And in a way, the one I'm talking about here is even simpler. And the point is, you use this transform matrix to compute partition function if you want. So you want to construct a matrix T. Okay, so here I will have a problem in that I will actually need two transfer matrices. But if you forget about this subtlety, you imagine I have only one transfer matrix. I construct it in such a way that my partition function will be T to the power 4 applied on the bottom configuration, and then I project onto the top configuration. And of course, with physicist notation, anything that is like this is this Hermitian conjugate or DAG. Yeah, I should have said I use DAG, which is a Hermitian, my notation for Hermitian conjugate. Okay, so if I go back to perhaps the picture from before, I construct my transfer matrix such that the number of dimer coverings with this bottom boundary condition and this top boundary condition is given by essentially T. There is T prime here, but you imagine T to the power 4. And this will, so I want to construct it in such a way that it counts exactly the number of dimer coverings. Okay, and this you can do. And so there are famous names associated to such method, like Onsager, Lee, Baxter, and many other. I'm not doing justice to the to this type of studies here. And so yeah, so I have this transfer matrix, and the point is you can show, I mean, it requires some checking and stuff, but you can show that this transfer matrix to do what I want to do, so to, for example, compute the partition function or any finer property of the model, I just need that this satisfies two identities. So the first one is that the transfer matrix acting on the vacuum is the vacuum. And this is for a very simple reason, is that remember when I was drawing my dimers, that there is a 0 when there is a dimer. So it means if I put the vacuum at the bottom, I put only dimers here, okay? And clearly, if I put only dimers here, this site here has to be occupied by a dimer. So it means I have to put a dimer here, I have to put a dimer here, I have to put a dimer. So there is no choice. If I act with the transfer matrix on the vacuum, which is this state completely filled with dimers, I have to fill it completely upwards. Okay, so maybe I forgot one here to have the same number of. Okay, so this one is easy to see, and you can check that to explicitly solve the model, compute the partition function or anything. I need another extra property, which is this identity. So that when I commute my transfer matrix with my fermionic operator from before, well, it generates term where my fermion at site I, if you want, on the edge number I, well, it goes to I-1, it can stay where it is, or it can go to I+1. Okay, so this, if you want, this generates the movements of my fermions. So I was drawing lines before, and it generates a possible movement for my fermions. Okay, and in a compact notation, I can write this as T acting on my fermionic operator is some matrix product with I can use the matrix Aij, which is an L by L matrix. So here it would be so L equals 6 here. So this would be, so A would be so T is a 2 to the L times 2 to the L matrix, and A is an L by L matrix. So these are different objects, but I need them both. Okay, and you can show using these fermionic variables that it's equivalent to the statement at the bottom, which is that to satisfy this commutation relation, I can write my transfer matrix as an exponential of a form which is quadratic in my fermions. Okay, and yes, and this is the point. And this is what in physicists would call free fermions. And free, why? Because it's Gaussian, if you want, in my creation and annihilation operator. So my CDI, and this is what makes the model simple. Okay, if I give you a more complicated model, I might not be able to write it like this. So it's if you want, it's a huge simplification which we will use in the following.
Here's the matrix. I'm sorry.
Yes.
Is the matrix A polynomial in U?
Yes. So here A is really simple. It will be something like there is 1 plus U square in the diagonal, and U. So it will be a matrix like this.
And the rest is 0.
Yes, and the rest is 0. So it's so you can so it has even a simple structure. Yes.
Thank you.
Yes. Yes, and the point is that where the transfer matrix might be in itself a complicated object, A is much simpler matrix, and in particular you can diagonalize it, and you can exploit the fact that you can diagonalize A to study this transfer matrix. So yes. Okay, so these are just so this is just a way to see this. I mean, I like fermions. I'm used to it since my background is more closer to condensed matter. So it's kind of, I mean, you give me a model of statistical mechanics. This is what I want to do with it. But it's related to many topics in mathematical physics, probability theory also. So, I mean, just to name a few, depending on your background, you might see that as some kind of, it's related to Schur function. Of course, free fermions is very close to determinantal point processes. What I talked about, you can also see as non-intersecting lattice paths. There are models in statistical mechanics that are related to this. And you can also study long-range properties in connection to free fields, conformality theory, and so on. There is also an obvious relation to integrability. So I won't say much about the integrability in this talk, but let me just say that if I write the transfer matrix as as explicitly dependent on this U parameter I was talking about, well, you can see that TU TV commutes. Okay, so TU TV is TV TU, and this is if you want a signature of integrability. I won't say more, but just to say that this is so it's not surprising that this model, which is free fermions, is belongs to a broader class of integrable model. It's a particularly simple example, but it has commuting transfer matrices. Okay, and so and since you have this transfer matrix, if you basically it's a quadratic. If it's a quadratic form in the fermions, you can completely diagonalize this matrix. And here, so I assume for simplicity that I'm on the infinite lattice. Okay, if you're not happy with this, I could also make a finite, the horizontal direction finite, but with periodic boundary conditions, or I can even relax that. But just let's say, for simplicity, I have, and my model is obviously translational invariant with respect to the horizontal direction. Okay, so if you allow me to introduce these operators, which are Fourier modes, if you want, of my creation operators, well, I can completely diagonalize this in the sense that I can rewrite the transfer matrix using this form. And you see now the index are the same. So it's C dagger K, C, K. Or another way to say the same is that if I commute T with C dagger K, it almost commute, except I pick up some factor, which is this exponential epsilon. Okay, and as I said, T is the exponential of a quadratic Hamiltonian. And so in condensed matter language, this is a free fermion Hamiltonian, with no pairings terms. It's a free fermion Hamiltonian with just some dispersion epsilon of K, which I can determine. Okay, and if for the dimer model, it's an exercise, and you can show that with my U parameter from before, the dispersion relation is given by, so epsilon of K is given by this formula. So this is so if you want, it's a tight binding model of fermions with some dispersion, which is from condensed matter perspective arguably a little bit weird because I mean, it's not nearest neighbor hopping. They are longer range hopping. They decay exponentially fast with distance, but who cares? This is what I get, and so I get a free fermion Hamilton. Okay, so far it's all very well known. I hope the people that know very well these techniques, they didn't fall asleep. But now that I'm doing this to describe statistical mechanical model, you might wonder about the following question. So, okay, I'm using fermions, and fermions, there are minus signs hanging around everywhere. So why is this supposed to describe a positive model? Okay, so the model I started from has all positive probability. So it's not obvious a priori that if I treat it with my fermionic techniques, I don't run into some kind of contradiction. That's somewhere I get minus signs which are not supposed to be there. Okay, so you might wonder, why is this positive? And for dimers, you can, so for the model I talked about, you can really easily show that the fact that it's positive follows from this relation. And the important point about this relation is that the fermion at site J, if you want, can only jump right to the left, if you want, stay at the same place horizontally, or go to the right. So it means that if I apply T on, let's say, C dagger 1, C dagger 3, I don't know, something like this. So on a state like this, where 0 is my vacuum, well, there is no problem, because if I act with T on the C dagger 1, I get something like C dagger 0 plus C dagger 2, okay, C dagger 3 on the vacuum. And this is C dagger 0, C dagger 3 on the vacuum plus C dagger 2, C dagger 3. And you see the point is you never change order. So you started with some orders for your fermions. So here it's important that I act with 1 and then only with 3. And if I apply my transfer matrix, I commute it. Sorry, I forgot to, I can do it like this. I commute it, and then I use the fact that T on the vacuum is the vacuum. Then the fermions, they never change order. So I'm never in trouble. This is fine. I always have a positive elements. And so it means for any state of the form I wrote, so some kind of fermionic states acting real space on acting on the vacuum, I have never any trouble. Every matrix element is positive, so I'm fine. And you might wonder what's the generality of this. So this is a slight detour through some kind of old complex analysis, I think, results. And you might wonder, what are the positives? So I reformulate everything in terms of my dispersion, okay, which for the dimer model was 1 plus u squared plus 2u cos k. Okay. And you might wonder, well, what are the positive dispersion? Because some might not be. Okay, if you allow longer range jumps, then maybe it's not guaranteed that the fermionic order stays the same. And there is a theorem which is due to Adrey and Thomas, which completely classifies this. Okay, so I will go through it quickly, but basically I just tell you the result. And the result is that there are very, very few dispersions that give a positive model that are compatible with, if you want, probabilistic meaning for my model. And these are positive linear combination of 1 e to the ik, e to the minus ik, and these logs, which we saw so this 1 e to the ik, e to the minus ik can come with any positive coefficient. And the one at the bottom, they have to come in with a positive integer coefficient. So this small subtlety, but basically that's it. And you see that those two logs, I need to reproduce my dispersions for my dimers on the honeycomb lattice. Okay, so it's fine. It means, as I was expecting, the dimer model belongs to the class of positive model. Okay. And this is a sort of, this observation is well known in the context, I think, of determinantal point process, but here I just backported it, if you want, to fermions, but it's the same. Okay, so this is the end of my very long introduction, and this is, if you want, what I have in mind. So this is what I have in mind. And so, since I already spent quite a bit of time explaining, let me go quickly through the other ingredients. So this is the first ingredient. These are my fermions. And the second ingredient are called limit shapes. And so one famous example, I will give you the most famous examples of limit shapes. So it's for dimers, but on a grid which looks more like a square lattice, and which is called the Aztec diamond. So here I have a slightly different color codes, but my dimers, they are, so here I just made the dimer appear, okay? There are a bunch of colors, but forget about them. They are just to make the picture look nicer. But this is, if you want, so I drew my dimer very, very thick here. And this is, if you want, one dimer configuration. So this is one example of, so there are many, many ways to cover this lattice. I could have found many other ways, but this is what I can, okay? And this is called Aztec diamond. And this is a reasonably small Aztec diamond. There are not that many lattice sites. I forgot, maybe 32 or 64, something like this. And you might wonder, and this is really picked at random. So here it's completely uniform. So I just picked out of the several, many ways to cover this lattice with dimer. I just showed you one picked completely at random. And the funny thing that happens is that imagine I look at a much larger and larger lattice. So I increase, if you want, a number of lattice points in the same region of space, because I want to show it on my screen. And if I do that, I increase it, and this is the best I have, I think. And you see something which goes under the name limit shapes. And what this means is that some positions for my dimers here on this region, they do not fluctuate at all, even though I drew it completely at random. So this is a typical configuration. Well, it happens that on the left, on the right, and at the top and at the bottom, the dimers, they appear completely frozen. So they are deterministic. It means in a large, when the number of lattice sites goes to infinity, basically, I have probability 1 of having, so here, for example, if I'm not mistaken, with probability 1, I will have only vertical dimers here. So they will be arranged like this, I think. Okay. And same on the right, at the top, there will be a horizontal with probability 1 and so on. So this is called limit shape. And this one has a particularly, I think the authors of this paper, they found a particularly nice name for this, because you can prove actually that the dimers, they are frozen. So they have a certain orientation with probability 1 outside of a circle. And since they are frozen outside of the circle, they called it Arctic circle theorem. And this is, and you can study this. There are lots of literature, both in math and in physics. Okay, so this is this now. So this was the famous example, if you want. But you can do, you can play a similar game with my dimers on the horizontal lattice. So here I choose a particular boundary condition, which I call domain wall. And domain wall is a bunch of 1 on the left, followed by a bunch of zeros on the right. Okay, and so pictorially, this means the lattice site along this, they are empty, they have no dimers, and those along here, they have a dimer. And just if you want, by just looking at the rules of the dimer model, you can easily determine that this one will be uniquely determined, also this one, and so on. So all the dimers shown in blue, if you want, they are uniquely determined by the boundary conditions at the bottom and at the top. And so it's, if you want, it's trivially frozen. What is more interesting is what happens here. Okay, this is a question mark. I don't know if it's, yes. That's visible. Okay, and so, and of course, with this transform matrix formalism, you can study it. And this is an example of a configuration. So with the same colors as in my introduction. So in blue, there are the dimers, and in red, there are my particles. And you see, these are a collection of particles. That's okay. So the one on the left doesn't do much interesting. It just goes straight ahead. Basically, it zigzags, but straight ahead. And the one near the last one, if you want, and it goes like this, it goes to the right, and then it comes back because it has to be compatible with the state at the bottom. So these are, once again, a collection of trajectories. Okay. Yes. And this is my this is what I want to study, and you can and so this you can study with this transform matrix formalism. Okay, so you have the top and bottom boundaries, and you just need some coordinate system to to keep track of everything. And so I use the coordinate system where y will be my variable for the vertical direction. Okay. And it goes between -r and +r, okay, and x labels horizontal direction, okay. And if I do that, I can use my transform matrix formalism, my fermions, and I get that, for example, the probability to have a dimer at position x and y would be given by this formula. And then you're very happy because you can use well-known fermionic techniques, in particular Wick's theorem, which allows to simplify lots of calculations. Okay, and in this particular case, since I'm looking at a model with a big number of fermions, basically it means this type of observable, this probability nxy of having a fermion at position x and y, which means probability not to have a dimer, sorry, at position x and y. I can compute it exactly, at least compute it exactly. You use these fermionic techniques, and this reduced to some determinants. Okay, so this is what you get. So for free, if you want to get at interesting observables, they will be given by some determinants, which hopefully you can compute. Okay, and this is an example of an average density profile for U. So for U equals 1/2. And this is what you get in the limit where so in the scaling limit where well, as I show in the last sentence, so R, so here it's -R, here it's R, and I take a scaling limit where R goes to infinity, so my lattice has infinite size in the horizontal direction, and I rescale x and y by R. So in this limit, you get an Arctic ellipse. So it's very similar to the Arctic circle from before.
You fix on, I'm sorry, Jean-Marie. You
yes.
only fix the boundary condition on the top and the bottom, right?
Yes.
The Bra ket psi 1 of the previous slide was
yes.
on the very top and
so this, yes.
And you take a half empty, half dimer.
Yes, exactly. So green, yes, and you see green means 1, so it means probability 1 to have a dimer. So it's exactly this. I mean, one probability to have a fermion, which is a non-dimer. Okay, so it means exactly what you said. Does that answer your question?
Yes, totally. Thank you. And the various color is the probability.
Yes, exactly. And so you see that 1, which is green, means completely frozen here. And yes, and 0 means probability 0 to have a fermion. Okay, and if you have a probability 0 to have a fermion, it means you have probability 1 to have a dimer. Okay, and this is so the same. You get frozen regions, and they are non-trivial. So they come out of some long calculation. Okay, so this is well known. I just gave you an example. So another example. So this was before I discussed my dimers, but if you remember from a few slides before, I told you there are many positive dispersions. And since I told you that you could also make linear combination of e to the ik, e to the minus ik, well, most certainly, if I am allowed this to get still a positive dimer, I can do cosine, because I just do e to the ik plus e to the minus ik divided by 2. And you get a similar phenomenology. So with the exact same boundary conditions, here the color code is a little bit different, but it's the same. I get an Arctic curve, also the same. And in that case, it's a circle. And this has been studied in a slightly different context by Prehofer and Spohn, more in the context of growth models. But you get the exact same phenomenology. And epsilon of k equals cos k is fine because from the, as I said, from the theorem I was talking about before, no problem. This is all positive, so it's a legitimate model is statistical mechanics. Okay, and now I come at my point, which is, if you want, this kind of not stupid question, but a very naive question. You say, okay, so you have cosine, this is fine, or for my dimers, my log was fine. But what happens to this phenomenology if you, on purpose, choose a dispersion which is not fine, which is not guaranteed to be positive? Okay, so I can do that in my formalism. I can do that because epsilon I put by hand in all my formula. So I can choose whatever I want. I'm not bound to a statistical model with positive Boltzmann. And you can wonder, well what happens with this? And this was basically, yeah, so I'm almost, I think I'm 40 minutes in. And this was, so if you want, this was what we had in the background. And this is the question I want to ask. What happens if I look at dispersion which are not positive? Okay. And I can look at this picture. And so this is a result of a simulation. So, and I pick an alpha, which I would say is strictly positive. Okay, because if alpha is 0, I'm back to cosine, which is fine and positive. Okay, so I do that. And so this is one simulation with alpha equals 115. Maybe this one is nicer, 1/4. And you see, I get, so this is a simulation. I just do it on the computer. And you see, I get similar phenomenology as before. Okay, there are still my region with probability 1 here for fermions. Here, 0 for fermions. Here it fluctuates nicely. Okay, fine. And then I get these red regions, which we call, so for lack of a better word, we call them crazy regions. And in this region, the density of fermions is not a positive number anymore. It's not in 0, 1, okay? So all the other colors, they are fine, they are in 0, 1, but if I take this large lattice limit, so this is a simulation, so I cannot be completely sure, but that's it. Here, I get those regions where the density is not in 0, 1. And if you really make a plot, it's even worse like this. It oscillates completely widely in these red regions. And if you want, this would be 0, 1, and this would be rho x, y. So the density of, so you see, it's not at all in 0, 1. It oscillates widely. It can do whatever it wants. And this is what we wanted to understand. And also, so it means there are regions where actually interpretation of positive statistical mechanics, probability theory doesn't make any sense, but for some weird reason, somewhere in this picture it works. There seems to be no problem. And okay, so to understand, to go back to this origin of this minus sign, you can use the Fermionic formalism to see that where the problem lies with cosine 2k, the term cosine 2k. So I already alluded to this before. Okay, so these are like notations for if you want imaginary time evolution. So my transfer matrix is exponential of some number tau, which can be whatever you want, times the Hamiltonian. And basically, in the end, it will boil down to the fact that if I act with this Hamiltonian here on my domain wall state, well, since I have a term cosine 2k, it might change some signs. And this occurs when, if you want, imagine there is, so I told you there is a bunch of ones, then there's only zeros, okay? And the problem is that if this fermion here hops by 2 to the right, then I get a minus sign. Why? Because I change order. Now they are not ordered anymore, and I have to pick a minus sign. So you see why there is a problem, and this minus sign, which occurs only for cosine 2k, occurs. Okay, and so it means that if you use this formalism, the probability to have a given configuration along a given horizontal line. So imagine I'm back to my lattice like this, and I imagine it's a given horizontal line. So C is the full configuration along the horizontal line, which is given by this formula. If I use the formalism, it can be negative. So there is no, so it's not, so I use the probabilistic term here, probability, but I should not be allowed to use this notation because it's not positive. And it's positive only, it can be negative, but I just, okay, I won't talk too much about it, but if y equals 0, which means, so since my boundary are at minus r and at plus r, So still, if I'm in the middle, I'm fine. And I'm saved by the fact that I get my terms which can be negative, but they are always squared. Okay. So if you play around with this formalism, you see at y equals 0, it's always fine. Okay, so I should perhaps mention quickly that so I told you if you compute with fermions, in the end you get determinants, which hopefully you can compute. It turns out there are very few boundary conditions for which we can compute things exactly. And those are, so this was the one I talked about, but we can also solve other boundary conditions which are more diluted on the left. So for example, instead of having only ones, you have 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0. So if you want, it has density 1/2 on average on the left, 0 on the right. And we can do 1/3 also, 1, 0, 0, 1, 1, 0, 0, 1, etc. So, I mean, which perhaps is better said by the sentence I put on the slide. One fermion every n sides on the left, and then no fermions. Okay, and so far, the motivation for these boundary conditions is that I can solve them exactly. If you give me other boundary conditions, I don't know necessarily how to do it. Okay, but so you can solve this, and okay, so since I don't have much time, perhaps I will skip about the technical part, but so it's using reasonably standard techniques, which are known to probabilitists or integrability also. You can compute this, you can find an exact formula for the density of fermions, and it's given by this not so nice looking formula. But basically, you have a double integral of something which is explicit. Okay, it's ugly, but explicit. So this phase I get here and this phase here, they are completely explicit. They are given by this formula. They involve the dispersion and something which can be deduced from the dispersion. Okay, and you see there is also this. So there are a bunch of formulas, but it's completely exact. I have this double integral, and the point is, in principle, I can study it because at the end of the day, it's just a double integral. The point I want to make is that this formula, yes, works only for my psi n, with one fermion every n side, and then nothing. If it's a more complicated initial or finite state than this, then maybe stuff can be said or done, but it's not obvious how you do it. You see already the formula is not so simple, but it follows from standard techniques. So just one slide to tell you which techniques I use. So okay, so this will, I apologize, this will be very very sketchy, but basically, if I give myself some initial states which are a bunch of fermions acting on the vacuum, it's reasonably easy to show that anything I could be interested in would be expressed in this form. Okay, so where I use once again my transfer matrix formalism with quadratic fermions everywhere, and you can show by Wick's theorem that this is a ratio of determinant. And it turns out that you get a ratio of determinants where there is a matrix M which appears at both at the numerator and the denominator. And by some miracle, and only for my initial states that I told you about, this matrix M is a Toeplitz matrix. Okay, and so Toeplitz matrix means the matrix element Fij, if you want, they only depend on I minus j. Okay, and this is a huge simplification. There is a I mean, it's well known in math how you can study such objects, and you can explicitly invert it and use this inversion formula to get an exact this double contour integral formula. So I mean, there are lots of steps, but you can do it. If the matrix is more complicated, then I'm stuck with this ratio of determinant, which I can't necessarily do much with. But okay, just to tell you that this can be done, and this is so in this business of limit check, this is, if you want, a reasonably standard technique. There are other ways to do it. You can use bosonization also to get it. Okay, so I think, so how much time do I have precisely?
Well, depends how many questions you want, but
okay, so maybe let me wrap up in 5 minutes.
10
maybe.
minutes.
Yeah, yeah. 5, yes. Okay, I think I should be. Yeah, so this is okay. So this is the less fun part. So I put it on the slides, but this is the less fun part of the project. I mean, but it's also the real part, if you want, is that this contour integral I'm talking about, you can analyze them analyze them using saddle point techniques. And just to tell you that depending on cases, so this is my representation for the saddle point. Okay, the argument is a little bit complicated, but basically by contour deformation and stuff like this, you can study these limit shapes and get the density profile I was showing you in the pictures. So this is how you derive this one. So this is one way, if you want, of deriving this Arctic circle types theorem. And since you have a contour integral, it's completely rigorous. I mean, you can do it. Okay, if you're a physicist, perhaps you won't be that careful, but it's reasonably well-defined procedure. Okay, and the point is that with my cosine 2k, so this is just to tell you that there are cases where this works fine. And basically, for a reason which is a little bit technical, and I won't go into too much detail here, with this cosine 2k, you run into a problem that you have 4 saddle points. And when you have 4 saddle points, turns out in some region in parameter space, the density can completely blow up. So you have no guarantee that it's between 0 and 1. And you can actually show that in the limit I'm looking at, it just diverges. So you have an exponential blow up. Okay, so this is, perhaps you won't see it from the picture, but believe me that if you do the saddle point analysis carefully, sometimes things go wrong. And so we could compute. And so, for example, we could compute exactly the region where things go wrong, okay? And this is given by this violet curve. And the rest is a result of a simulation. So the match is not perfect, but it's just because the simulation, they are limited to finite size. So we are pretty confident that if we were able to simulate larger R, because this is still plus R minus R, this would go to this violet curve. So if you want to have a characterization of the regions which are fine and the one which are not. Okay, and so now I'm close to finishing. Okay, so just to repeat that the argument I gave before, that the problem occurs because the one can jump around another one, and then you pick up a minus sign. So at least as a level of physicist argument, if you want, you say, yes, so there you need the one to jump around another one. So maybe the problem occurs only in regions where the density is high, okay? Because of course, if you imagine a configuration, let's say where there is only, there are many zeros, there is one, and then you have to wait many zeros to get another one, then this will never occur. You won't ever get this problem. So the idea is that the density, the problem might be caused by the fact that the density is too high. Okay, maybe if I lower the density, I might get something that has a probabilistic meaning. And this was the motivation for studying this psi2, psi-t, which has one fermion every 2 sides, one every 3 sides. And I spare you the technical detail, but the result, which is the simulation. So here, this was for psi2. Okay, so it means the fermionic boundary condition is 1, 0, 1, 0, 1, 0, 1, 0 on the left, then 0, 0, 0, 0. And we see, so this is a simulation, we see both analytically and in the simulation that there are no problems with minus sign. So it seems to give you a model which is a positive statistical mechanics. Okay, and this is if you want one of the main conclusions. So you get this from saddle point analysis, and you can check that it's positive. Okay, so so perhaps let me conclude briefly. So I didn't talk at all about this, but in some more mathematical literature, there is some a recent paper by physicists and mathematicians which studied this y equals 0 case. So remember that since I'm between minus r and r, and I told you there is no problem with positivity at y equals 0. So this has probabilistic meaning, which was studied in this relation. It's related to topics in probability theory, in particular this. So I won't have time to talk about this, but this occurrence of what's called Tracy rhythm. So there is a relation to random matrix theory. And so, yeah, so the point of this this project, which started more as a fun little question, is that there seems to be weaker forms of positivity. So I don't need to have only these specific dispersions to get a positive model if I allow myself to change boundary conditions. Okay, of my discussion here, another diffusion, my dispersion relation was always a scalar, okay? So it was just a function of k. But we didn't look at this too many details, but I'm pretty sure you can generalize this to many bounds. Okay, so you can study models that have several bounds in bound theory language, and presumably you will get a similar story. Presumably you will also get a similar story in the presence of interactions, so models that don't map to free fermions. But this is only a qualitative statement. So since already these free quadratic fermions things were not so easy to solve, this looks extremely complicated. But just to say that, I mean, at least from physics intuition, there should be a similar phenomenology. And with this, I think I'm right on time, and I thank you for your attention.
All right. Thank you, Jean-Marie, for a nice and interesting talk. So the talk is open to questions. Let's see if people have questions. So Yvan.
Very nice talk. Great, very interesting. You said you were able to compute exactly the case, one fermion on the left side, every n side.
Yes.
Could you do, for example, fermion, fermion, empty, fermion, fermion, empty?
This is a good question.
Because you could then try to measure when between 0 and 1/2, because the fermion empty, it's like half the density, and you don't see the crazy regions. Where does it start?
Yeah, so this is a good question. And so right now, so I suspect it's doable. Yeah, because it's basically if density is 1, problem is there is a problem. If density is 1/2, problem is fixed. So where is the threshold?
The threshold. Yeah.
And, yes. So and this is related to perhaps partly to our ignorance of the techniques I was alluding to in these slides. So if I do, for example, so what you would like to do is like fermion, fermion, empty, fermion, fermion, empty. Something like this, right? So if you do that, you still get a Toeplitz matrix. So the matrix still depend only on I minus j, but it's by block. So it means if you want my matrix is a bunch of 2 by 2 blocks. Okay, and so on. And it's only so if you want, it's like because a Toeplitz matrix would be like something. If you want the matrix element would be M0 in the diagonal, M1 in the upper diagonal, M-1, and so on. And here this would be a 2 by 2 matrix, which I don't know, called A1, so it's Toeplitz, but only by block. So in mathematical parlance, I think they would say the symbol is a 2 by 2 matrix. And you run into some difficulties. So I suspect maybe these difficulties can be solved, but I don't know how to do it. So it's a technical problem which probably can be overcome. I mean, if you're a specialist on symbols that are matrix, then maybe you could be able to solve this. And I suspect it's possible, but we didn't. Okay, we didn't try too hard, but it's not completely obvious how you do it.
Merci.
Okay, we have other questions. I have a naive question. So if you start, instead of 2D dimer covers, you want to study 3D dimer covers, there, this Jordan-Wigner transformation, you can imagine doing it by doing a snake on your initial condition, the bottom plane. So
you would have like, I don't know, like, let me try to draw somewhere. you would like a 2D plane, like
Your triangle diameter covers on some three-dimensional
yes, or something like this.
lattice.
Yes.
But yeah, I'm not sure. Maybe none of these. Maybe some of these tricks actually fail in this case.
Yes. So the mapping to fermions might fail, for the same reason that Jordan-Wigner transformation doesn't work in 2D. I think.
Yeah, but I mean, in certain cases, you can define a Jordan-Wigner if you sort of define a long snake that goes around your 2D base plane.
Mm-hmm.
But then it's like a non-local transformation because fermions that are sort of nearby can be very far on the snake. But so maybe this method doesn't work or hasn't been tried, but have people studied what limiting shapes you get in that case? You get Arctic globe.
So there are models, there are 3D models that have been studied in this context, but okay, I think in most cases they map to some 2D thing at the end of the day. So I mean, a genuine 3D limit shape problem you can study for sure numerically, but I think so numerically, yes, I'm pretty sure it can be done. But I don't think there is much literature on this in higher dimensions. Yes.
Okay.
Actually, people did that even, I think, for quantum dimers, because you can, this limit shape problem, you can ask the same with quantum dimer Hamiltonian. And I think there are some numerics paper, physicist paper, which look at this and define limit shapes also. But yeah.
But that's for these 2D.
Yeah, but but still stick to 2D. Yeah.
Mm-hmm. And I guess if you swap your dimers for singlets, which are not orthonormal, orthogonal.
So phenomenology will be the same. Yes. It's the same. So there are people studying also interacting dimers, which is similar to RVB business. For example, you can put, and even this has been studied in mathematics literature. So you have these dimer core-rings, for example, on the square lattice, and you put an interaction term that favors parallel dimers along the plaquettes. So you can do that, and there are even theorems that prove that there is a qualitatively similar behavior if you add small interactions. And so this interacting dimers, I think, is very similar to let's say RVB type states. And so but for RVB nobody has done it, but presumably you could draw Arctic pictures. Yes.
And trying to sort of map this to the quantum language, this would be when you're evaluating partition functions, for example, or
sorry, can you repeat? I didn't hear very well the question.
Yeah, I'm just not used to this type of formulation in the quantum formulation. So what you want to?
Well, I mean, in the end, it's 1 + 1. Okay, maybe I'm exaggerating a little bit, but it's like Feynman path integral, except it's exact on the lattice. If you want.
Yeah. But these Arctic shapes in the Feynman integral language. So I guess knowing where they are helps to evaluate the given path integral. Because
So so for example, what I never talked about. So I always drawing this picture, and basically with fermion density 1 on the left and 1 on the right. And if you want, this is like order 0 kind of thing. It's just what are the dimer orientation. Or if you want, if you think of some spin chain, let's say, it's just like I tell you the magnetization, if you want. So it just, but here inside it fluctuates. Okay. So what I talked about was really at the level of just density profile, or if you want magnetization profiles. But of course, inside this, it fluctuates, and it's described by some field theory. Actually, it is described by free conformal field theory, so free boson, if you want. And so, but you can use this background, this non-trivial density profile, because here it's 1, here it's 0. But if I were to draw a density profile, I would see something like this. So where it's 1 outside the fluctuating region, and then it varies slowly. And I don't know if that's your question, but the interior of this disk, there are long-range fluctuations described by massless field theory, and you can also study it. And there are a few references that do that. So if you want, what I talked about is really order 0 before going to, because you could argue that fluctuations are more interesting than just the limit density profile, but it's like step 0 if you want.
Mm-hmm. Yeah, okay. Thank you.
Yes. Actually, it gives some kind of cool stuff, because inside you get usual free field theory, but you have curve space.
Can you get?
Yes, you get. So you get a CFT. So the interpretation is you get a CFT, but it's in CFT in curve space because of this non-trivial density profile. So you cannot do like usual CFT in condensed matter, where you start from some uniform background and then you look at small excitations. Here we look at small fluctuations around some non-trivial background. And it turns out the way to tackle this is to make it curve space. So if you want, the coupling constant depend on position. And yeah, there is some literature in this. I even participated earlier. But yeah, it's kind of
curve space time, I guess, or Euclidean space.
Yeah. So here it's a completely it's Euclidean. So it's curve space time, but time is imaginary. Yes, and also in mathematical theory, I think from mathematicians, this is well understood. They don't formulate this as curve space-time field theory, but they talk about Gaussian free field, and there are a bunch of results, in particular by mathematicians. So I think including people like Kenyon, Okunkov. Okay, so that's more for the limit shape, but there are several results in the mathematical literature which are very related to this curve space field theory. Yeah.
Okay, thank you. It's interesting. And if we don't have more questions, or if we do, I think we can thank Jean-Marie for answering the questions and giving a nice talk. Merci, Jean-Marie.